Good. Well, so we're going to continue talking about symbolic dynamics. And just to entice you, in the SAGE published area, there are these two interactive labs that you can play around with that just show you how the symbolic dynamics works and goes through that construction of which sequences can follow from which sets of initial conditions. So it constructs the refined partition. So play with those. And we're going to deal with some of the generalizations of Markov partitions today. Markov partitions are a little too constrained. And then I don't want to leave you with too rosy a picture. In some sense, the largest lesson here is that it's cautionary tales for when we measure things. In particular, how we measure things interacts with the dynamics. And so I'll show you a generalization, or well, I should say generalization or kind of a relaxation of the Markov condition after we do one example in higher two examples in higher dimensions, called a generating partition. And then I want to work through some examples where it's good to give the flip side. How could you badly partition something? We'll work through a case like that and come up with something you're already familiar with, it turns out, and that we'll analyze again and again. And then pretty much at the end of today's lecture, we're going to be over here just dealing with these processes, over time series. We've made the argument, we're making the argument and ending that today about how we go from a hidden continuous system, how a measuring instrument interacts with it can give you, even for very low resolution instruments, very precise information about a nonlinear dynamical system and how chaotic it is, but also how instruments distort. And then we're sort of done. Then we have this we're just presented with a process. And so the next lecture is going to shift yet again into talking about information theory. What can we extract? If I give you a set of sequences and their probabilities, what can you learn about how the process is structured? So we're going to yet again have this big shift in focus, right? And hopefully at that point you'll start to get some sense of this very high level view, how we're borrowing ideas from different areas, dynamical systems, symbolic dynamics, information theory, and then theory of computation, and putting in this much larger narrative about what's going on in this measurement channel. What are we doing when we do science? This is a little bit of a cartoon, but at least we're trying to see how these different specialties relate to an overall picture about how we can learn something from the measurements we make in an experiment. Okay, so the story continues. So I want to talk through, not calculate in detail, but sort of talk through how this Markov condition generalizes to higher dimensions. We started with one-dimensional maps. And if you remember, the condition there was that you make some hypothesis. Here's some candidate partitioning of the state space. So think about the one-dimensional map. And then there's things you have to show, mainly that the map operating on every partition element, the image of that under the dynamic is the exact union of other elements in the partition. So it's like boundaries match. And that the map is monotone over those cells. Right? And the benefit of showing those was that then you can use the process that's induced over the partition labels. You now have this discrete symbol process, and that is actually a Markov process, an order 1 Markov process. And we can calculate all sorts of things from that. So we go from this, a mapping over infinitely precise points on the interval and this perhaps very complicated nonlinear function to just studying symbol sequences, right? So in the symbolic dynamical system that's induced, the dynamic is trivial. You're just shifting the time index on the sequences, and then you describe the sequences that can be produced with this Markov chain. You get a matrix, eigenvalues, eigenvectors, boom, you're done. And this was, in fact, historically the first way that people had of talking about how chaotic these complicated nonlinear systems were, like the three-body problem in mechanics. it was practical in a sense, but it actually is in some ways kind of deeper when we put it in the context of a measurement theory. What do instruments give us? So question, how does it generalize to higher dimensions? And that actually wasn't known. It was all particular cases for a very long time, or very, very formal, that these partitions existed, non-constructive proofs that these things existed. So what I want to do is show you the generalization of that Markov condition for one-dimensional maps to, well, higher dimensions, but we'll talk about two-dimensional maps. We'll do the dissipated Baker's map, and then the cat map, or the toral automorphism. Remember the Poincare stretching? We'll show you how we can partition that up. Okay, so this is going to take a little bit of time, and so that's why I'm sort of preparing you. What I'm going to do is talk this through and not do detailed calculations about how it works, but give you some sense. And if you like, it is straightforward. The calculations just become a little bit kind of tedious. In fact, maybe we can talk about what kind of software we want to write to do this automatically. Anyway, so here's the idea in sort of any dimension. So the idea is we have some candidate partition, and we say it's Markov when, for all the points in a given partition cell that map to an image in some other cell j, so we're going from I to j, so here we have x, so here's piece of I, and that x maps over here to cell piece of j. Then there's a condition. The Markovian condition is not so much on the cell boundaries, but on how the stable and unstable manifolds carry forward and then match. Okay, so here's the idea, and I'll say it graphically first, and then kind of go back and interpret what the symbols are. Okay, so here's here's x in partition cell I. It maps over in partition cell j to f of x. Back here in partition cell I, we have its unstable manifold and its stable manifold, and we can calculate that at least locally, or if the examples that we're going to choose are uniformly hyperbolic. This decomposition of stable and stable manifolds is nice and well behaved for every point in the state space, and uniformly so. Makes the construction much easier. Still sort of surprising. Okay, so here's the unstable manifold in red. Goes off like this. And then what I'm going to look at is the unstable manifold of X, the red and black, and then intersect that with the cell. Okay, so this object here is just this piece here. And then what I'm going to do is take F and apply that to this set. Well, if it's the unstable manifold, it's going to stretch. And essentially the idea is, in the unstable direction, the mapping of this set of points in red contains the unstable manifold of the point f of x, which would be this thing going way out here, restricted to pj. Okay, so I can say it the other way. So here I am at this point, the image of f of x. I have this unstable manifold of f of x goes out here. I restrict that to this pj, and that has to be inside of f of x's unstable manifold, which is in red. So it's kind of a containment condition here. There's a symmetric condition for the stable manifold. So I look at the stable manifold of x, intersect that with cell I, and that's just the blue part. I mean, the unstable manifold goes out here, just the blue part. Then I look at the image of that, and then the idea is that that's contained in the stable manifold of f of x, which would be out here, restricted to pj. So this guy maps for, it's the shrinking direction, so it shrinks, and it has to be inside of the stable manifold f of x, restricted to pj. So in some sense, the stable and unstable manifolds, as they map forward, have to sort of respect each other and map onto each other. Now again, this sort of is, why does this work? That requires quite some time to establish. Instead of spending 2 weeks proving that that's the general definition, let's do 2 examples. One kind of straightforward and familiar. So we studied before the dissipative Baker's map in 2 dimensions, right? In the sort of horizontal coordinate, x coordinate, it looks just like the shift map, 2 times x mod 1. right? And so that's taking the square here, the unit square, and stretching it out by a factor of 2. And then in the y direction, we shrink by this proportion a, each of the pieces. So we stretch it out, we shrink it down by a, and then we cut it in half and stack, in this case, the green on top of the yellow. So before, I was just using green and yellow to indicate that this piece went up here and the yellow piece went down below. Right, and so we do this again and again and again. So this was, labeling as A and B was just kind of something to guide the eye. That all the states here went to this lower piece and all the states here went to this upper piece. Okay, so now what's the Markov partition for this? Well, so we just sort of hypothesize that, in fact, A and B, the yellowish and greenish areas, are the two different partition cells, call them A and B. Okay. Now we have to convince ourselves, and this is where you kind of roll up your sleeves, but at least visually, that every point in A satisfies that condition as it maps forward, and every point in B satisfies that condition. So what does that mean? Again, so here I'm picking some x in A. Here's its unstable manifold restricted to P sub A, if you like, the A piece. I map that forward. Well, as we know from the map, it's kind of simple. This is of width a half. When I multiply it times 2, it actually stretches over the whole interval in x, and therefore is contained in the unstable manifold of f of x, restricted to the next partition cell element, which is B. And then same argument here, complementary argument with the stable manifold. Remember, we're shrinking vertically. This blue piece is the stable manifold of x restricted to PA, to the A. I map that forward, but that's being shrunk down and stuck down here. And then that's contained inside of the unstable manifold of f of x. And then what's the benefit of this? Just like before with the one-dimensional maps, we have now these two partition elements. So we have verified that we can summarize the continuous dynamics with the two states. And then in addition, we can look at what state transitions are allowed to get the dynamic out. So A can go to A, right? So that's the light yellow piece of A maps to this, all the x values less than a half. So A goes to A. There's a piece of A that goes to B. There's a piece of B, kind of bluish teal colored, that goes to A, and a greenish color that maps to B. So all transitions are allowed, and we summarize that with this Markov chain. Again, the claim is that now if you look at A-B sequences, that's a faithful encoding of the evolution of basically any point under the Baker's map in the unit square. Quantitative properties, we want to know about the Baker's map orbits. We can answer by calculating various properties of this. In fact, the information theory we're going to start introducing next lecture will tell us that there's some more properties we can calculate than we've talked about before using these state-based models. Okay, so yeah, Greg.
Concept check. So if you had the full history then of your Markov chain, could you, of the output state stuff, could you figure out exactly where it's
Yes, yes.
So only if you have the full history.
Well, okay, if you have a finite sequence, then that will be some region.
Yeah.
But part of the establishing the Markov partition property means that the area of the associated set of initial conditions that correspond to some A-B sequences, that area goes to 0 as I look at longer and longer sequences. So then asymptotically, there's this essentially a one-to-one mapping. I mean, there are some, well, we'll talk about how some of this sort of messes up, but not too bad. Right? There can be a little bit of ambiguity in symbol sequences labeling orbits, but typically it's not too bad. Well, actually, I'll give you an example where it's horrendous, so I shouldn't say that. We'll see. But we'll talk about bad partitions. But this is good, and we're just talking about how to take the idea that we understood for the one-dimensional maps and generalize it to 2 dimensions. Okay, well, it's the dissipated Baker's map is almost constructed to be this straightforward. That's why it's kind of one of the first examples we study. Now, more interestingly, and this wasn't known until the early 60s, a little surprising given these ideas have been talked about for 60 or 70 years before that there's a Markov partition for the cat map. So again, remember, this is the, I use that for the stretching Poincare picture, just to kind of demonstrate what exponential instability meant. So it's sort of straightforward. It's just this matrix here, 2, 1, 1, 1 times the current x value, and then you mod, put it back into the unit square to get the next. So, and you probably recall this graphic, so this just explains how the map works. Here's our unit square. We have states in the square, they get iterated. So the easiest way to think about this is to break it into 2 steps. One is the matrix times the current point, and then the second is to mod things, stuff it all back into the square when things fall outside of the square. Okay, so the yellow here is the image of the unit square. In particular, the 1, 1 corner goes up here to 3, 2. Right? You can kind of see that, just put in 1, 1. The origin is always stable, right? If I put in 0, I always get 0 out. This point gets shifted over to here, and then this point down here gets shifted up here to 2, 1. Okay, so we have this kind of laid out, and what I'm thinking here is just looking at the extended state space covering it. But in fact, this is mod 1 in both x and y. So in fact, none of the points in A shift because we're still in unit square, but for example, if we're in B, well, the y values, the points here are between 0 and 1, nothing to do there, but the x values are between 1 and 2, so I shift this over here by subtracting off of 1, doing the mod. So the B piece shows up here. C, mod and mod gets stuck over here, and then D, mod, it sandwiches in here. So this is how the mapping goes all together. And then do it again. Right, as you saw, it took the Poincare image and just a few iterates completely scrambled. You could no longer see Poincare. All the colors were still there, but they were now scrambled in their spatial relationship, and we lost that initial information about Poincare. And we also talked about the stability analysis. So this is all going to come back and be really important for the construction. Right, so before we had basically just the eigensystem analysis of that 2, 1, 1, 1 matrix. We're doing a local analysis of some point in the square, and we want to know what are the stretching directions and what are the shrinking directions. So the stretching directions correspond to this eigenvalue, and then there's a companion eigenvalue that's less than 1, so that corresponds to shrinking. And the directions are given by the eigenvectors, the associated eigenvectors. So I've just kind of drawn it out here. So here's the origin. Notice that the lambda and the v's don't depend on x. So that's one of the things. So we're not changing the amount of stretching and shrinking as we move around the state space. And this makes this example particularly easy to analyze because it's not state dependent. So, but let's just focus on 0, 0. And so we have this picture that the unstable manifold goes off in this direction. It actually doesn't align with where your eye might think it should. And then there's an orthogonal stable manifold. I'm showing the vectors here, but this is contracting, this is expanding. And the rates are given by the lambda 1 and lambda 2. So red in the graphics I'll show you is the unstable manifold of some point, and blue will be a stable manifold at some point. Here, just the origin. Okay, but we already did that. So what was figured out in early 60s by this mathematician Ben Weiss. In fact, it's kind of fun to read this little paper where he talks about this, because very rarely in formal math papers do the authors ever say how surprised and excited they were. But this paper's kind of cute or amusing for that. He's like, "Wow, I didn't believe this would work." He knew there were sort of non-constructive proofs, but actually doing this. So what he did was he looked at all of the unit points here, which under mod 1 are all associated with the origin, right? We're thinking of this as periodic boundary conditions in both horizontal and vertical. And he just calculated out all their stable and stable manifolds. So I just talked about the unstable manifold and the stable manifold of the origin. I can also look at the unstable manifold of -1, 0, the stable manifold of 1, 1. They kind of laid this all out and basically just had a flash of insight that once you looked at sort of the various intersections and the subcells that you get from just kind of naively laying out the boundaries, the stable and stable manifolds, it suggested this pair of squares as the fundamental units, the fundamental cells of a Markov partition. So I'll talk through this again, it's straightforward. Remember, we're basically just trying to see that every point in here has this sort of, it's unstable manifold maps into its image, unstable manifold, things kind of align. So I'll just talk this through. But so hypothesis, it's not saying that R1 and R2 are, a Markov partition. It's not obvious at this point that this should work, and that's why he was so surprised. I would say almost giddy in his writing of the paper. And there are alternatives too, but let's just go through this one construction. Okay, so the first thing to note is that this is a partition of the state space, and the sort of you could go through here. Well, let me just say, I mean, every one of the corners here for R2 and the corners for R1, they're the intersection of a stable and unstable manifold. We know what those directions are, and therefore we can calculate exactly the point in 2 dimensions that are the corners. So we just, is this a partition? Well, you have to sort of 2 ways to do that. You might think, well, what I really should do is see all the pieces that fall out if they map back in and kind of fill out the unit square. The other way is just to look at this cover space, all the unit squares that's laid out, and to see if R2 and R1 tile. And they do. I mean, you actually have to calculate things, but the result is yes, it's a tiling of the plane, completely covers the state space. No holes. Okay. So here we are, and now it's a partition that has to be established. Now, of course, the real effort here is to figure out what the images of this look like, and if they fall kind of exactly back into themselves. Okay, so here is f of R1 and R2, and you'd have to convince yourself of this, but not too hard. You can iterate points. So claim. Here's R1 square here. It maps to this right here, and I'm denoting it f of R1. It's this long, thin, yellow image of R1. And then f of R2 is this piece out here. And when you look at it, you can see that, at least the boundaries along the unstable direction of the cells maps to the boundaries, or at least the stable manifolds of other points. So there's some hope. If f of R1 had gone just a little bit into here, you'd be very suspicious that this was good. So the boundaries are kind of aligning. That was the first thing he was looking for. That these boundaries here map to these boundaries here. These boundaries here map to these boundaries here. Okay. So, like I said, this is our candidate partition, and we have 4 points here. I'm just going to call them ABCD1 and ABCD2. I'm not squaring here. And so these are the 2 kind of written out explicitly. And we can calculate the coordinates of each one of the corners. ABCD1, ABCD2, for example. So A2 and B1 are the same. Here, I'm just differently labeled. And that corresponds, if you go back to the previous picture, to the intersection of the stable manifold of 0, 1 and the unstable manifold of 0, 0. Here. Okay, and then it's the unstable manifold of the origin and the stable manifold of 1, 1. Okay. And so on. And you just kind of go through and write this out for the other things. Just a bunch of algebra in principle that you could calculate where those points are. Now, another thing you want to test for consistency is that the image of these rectangles also tiles the plane. Well, we know that the whole map is area preserving because we calculated the determinant, which is just the product of the eigenvalues, and that was 1. So we have these things that are shrinking down and stretching out, and they preserve area, and they sort of match on these boundaries. So you can argue that they also tile the plane this way. But sort of more interestingly, let's focus in on, right, we have to, now we got this the images of the rectangle spread out over the two-dimensional state space, we have to see how they map back into what the relationship is to R1 and R2. So here's the claim that if I look at the image of R1 that is contained inside the union of R1 and R2, so this is maps to here and here, after I've kind of mod 1. So now we're kind of coordinate free here and just showing the relative relationship. And then the R2 maps to these three pieces, which is the union of R1 and R2. Again, all these statements require a little bit of algebra calculation to verify. In fact, there's a little more sort of fine structure here. So you kind of complete the establishing this as a Markov chain when you can look at how R1 and R2 map into each other. So what I've done here is there's another actually stable manifold that gives you the dividing points. What I've done is break R1 into two pieces labeled 1 and 2, and R2 into pieces 3, 4, and 5. And then so the piece of R1 that's labeled 1, that stays within R1. This other piece, all the points in the 2 section of R1, those are points that map to exactly R2. And then the same kind of analysis here. 3 are those points of R2 that stay in R2. 5 also stays in R2, but then 4, this middle piece here, is actually that part of R2 that maps to R1. And then once you use this sort of refined, just kind of an indexing scheme here, you can write down this Markov chain. I'm just labeling the edges here, pointing out the 5 different cases I give you. So, right, so R2 has 2 ways of going to itself, but if you started in this piece of R2, then you're going to go to R1. R1 stays to itself because this piece just maps to here, and then R1 goes to R2 on the 2, and so on. So that's a graphical description of how the construction goes. The algebra is, I said, just kind of tedious but straightforward. And you could imagine writing some code that would do this more or less automatically. Basically, rather than iterating points, you'd iterate squares and show that they kind of mapped onto each other, and you can divide them up this way. So straightforward, if a little bit tedious to show. So Markov partitions, the concept generalizes to higher dimensions. It requires a conspiracy of certain properties to have this work. It's a very Markov partitions. I mean, we're getting this great simplification. It's a Markov chain, order 1 Markov chain. We just do the algebra of this, linear algebra of this, and calculate all the properties. So that, sort of stricter constraints lead to sort of a simpler result. But it's just very, very unusual to find this. There's sort of general constructions for these simple linear maps on the unit square. You can imagine generalizing that to higher dimensions. So that all kind of works when it's uniformly expanding, contracting, uniformly hyperbolic, things like this. So there are classes of systems where you can do this. And it requires this sort of the boundaries respecting the stable and unstable manifolds and sort of essentially mapping onto each other. Well, that doesn't happen very often. So now I want to, I guess, give a little bit of good news that there's a simple generalization of the Markov partition, and it will correspondingly work with a larger class of systems. And then I'll kind of go through a number of cases where things kind of mess up, and then directly talk about how bad can it be if I just willy-nilly pick some partition without doing any kind of analysis. What could an arbitrary partition of a dynamical system lead to? So, okay, so first the good news. Okay, so the idea here, the generalization is called a generating partition. And if you remember, the main goal wasn't so much that partition cell boundaries map to themselves, was just that we had a good coding, that we had this faithful encoding, that the discrete sequences, as they got longer and longer and longer, were associated with some hypervolume of initial conditions that went to 0. So we had essentially an encoding from infinite discrete sequences and points in the state space. Okay, so that's the criteria that generating partitions focus on. not this more boundary to boundary exact matching idea. So much easier to find the Markov partitions, and I'll show you in the case of one-dimensional maps. It's a very simple rule. But again, the main criteria is that the set of initial conditions, the size of them goes to 0 as we look at longer and longer sequences. So these, again, the cylinders, remember, those are sets of infinite sequences that share some word label points in the state space as we go to longer cylinders. And I also emphasized last time the curious thing about this, and it was particularly easy to see in the one-dimensional maps, that this construction works. Having good codes actually depends on the system being chaotic. Right? So here what we're saying is I have longer sequences of observations, and that means that there's kind of this contraction property as I look back in time. The sets of initial conditions that could lead to that code get smaller and smaller as I look at longer sequences. That's the exact dual of the fact that in forward time, the chaotic systems are exponentially sensitive in spreading things out. You need, they go hand in hand. So, kind of interesting and positive aspect of chaotic behavior. It's not just all, oh, the world's unpredictable. In fact, sequences are more and more informative for chaotic systems about where they could have come from, what the initial states could be. Now, there are a few slightly messy things which I'm doing just a horrible job kind of racing over them. There are caveats in some of these things, but we're not going to go into technical details. It really depends on, some of these depend on what your, say, quantitative question is about the original dynamical system and how that's reflected in this discrete symbol sequence or a Markov chain. So if you want to calculate, say, how chaotic the system is, and we'll come back and talk about that in the context of information theory, and then connect that back to the Lyapunov exponents, then you can tolerate sometimes slightly bad mappings. So, for example, there can be sort of a finite to one mismatch between internal orbits and sequences. That's sort of okay if you're looking at asymptotic properties. Rates, per time step rates of instability, for example. One way to think about this is that, in the world of real numbers, we have a concept called 1. But when we essentially choose coordinates, namely decimal expansions, there are two symbolic labels for the concept of 1. Right? We have 1.0000 going off forever and 0.99999. So a decimal representation of the real number 1 is ambiguous. But that's finite to 1. I have two symbol sequences that correspond to the same point on the line. Doesn't usually bother us, right? That's okay. Same kind of thing here. What happens, you'll find this kind of ambiguity in the codings, if you study these in detail, when you look at points very close to the boundaries of the partition cells. Okay, so, but that's okay, it's finite to 1. Okay, so we're looking for these generating partitions with just this much looser requirement that it's a faithful encoding geometrically, that the set of initial conditions that can produce them gets smaller and smaller as I look at longer sequences. Well, Markov partitions are generating, have that property. And when we have a Markov partition, we got out this Markov chain, or the more technical way to say that is we partition up this continuous state dynamical system. And if you remember back to our discussion of how dynamical systems push probability distributions forward, there was that Perron-Frobenius operator. That's a continuous integral operator, and when we just do that over this discretized state space, we end up with this finite state Markov transition matrix. So there's actually kind of a way you have to sort of get through if you want to talk about the evolution of probability distributions, you start with the Perron-Frobenius operator over the continuous state space, in a sense, coarse grain that, and then we end up with this finite state operator, which is just our regular old Markov chain model. So again, that was good. Now, in the case of generating partitions, that happens. That's nice. Sometimes we'll have as the output the resulting process of the discrete partition cell alphabet can be some sort of finite state thing. But in the general case, we're going to get these hidden Markov models. That's why we introduced these before. And sometimes they're finite, internal state set is finite, and sometimes they're infinite. And in fact, they can be infinite in a couple different ways. Like countable infinity states or an uncountable infinity states. So we have to work with that. We'll build up to being able to calculate things in these cases. But sort of much more interesting. The processes that come out are, well, what does it mean if I have an infinite state, sort of Markovian or near Markovian? That means this discrete output process actually has infinite range temporal correlations. And so we'll have to learn how to deal with that. So how to measure that, how to detect that it's there, that sort of thing. Okay, let me back off a little bit, just some examples, and it's really very straightforward here. So before, when we talked about the tent map, we had it going all the way, taking the whole interval to itself, went all the way to the top. That was in the map, A equal 2. And if I had this binary partition, I could immediately verify it was Markovian because the 0 cell mapped to itself or to the 1 cell and so on. And then the map was monotone over each piece of that. But now, if I just pick an arbitrary height, doesn't go all the way to 1, it's obviously not Markov now. Bummer. Right? So 0 maps to itself, but then there's a piece of 0 that maps only to part of the 1 cell in the range of F. No good. So this isn't going to be a Markov partition. Turns out it's generating. So as long as the map has slope greater than 1, this simple binary encoding where the decision point, the boundary is put right under the maximum map, that is an encoding now in this generating partition sense of long binary sequences identify smaller and smaller sets of initial conditions. And there's that SAGE interactive lab where you can put in the tent map and see that it holds for that too at different parameter settings. Basically, for any parameter setting where the slope is greater than 1, this will be a generating partition. Okay, so only Markov at slope 2. Well, actually, if you remember the example we did, it's also Markov where 2 bands merge to 1, 4 bands merge to 2, and so on. So there are a few other parameter settings where you can concoct a Markov partition. But for the general sort of arbitrarily picked slope, parameter value A between 1 and 2, no Markov partition, so we sort of fall back and look at generating partition. Logistic map, basically the same argument. So before, we had a Markov partition when the map went all the way to the top, and that was the parameter value R equal 4. Other settings, well, band mergings it works, but just like the tent map, we need something else. And so it turns out this dividing the interval in half, right, underneath the maximum gives us a generating partition. So here's the general rule. At least for one-dimensional maps, we can make us a simple rule out of this. So if I just squiggle out some arbitrary f of x, a map I'm going to iterate. So we call the monotone pieces laps, historical terminology. So this is 1, 2, 3, 4, 5, 6 laps. The rule is to find a generating partition is that you put a partition divider underneath each extremum. So here, 6 cells. Basically 1 cell per monotone piece. And that'll be a good code. Just kind of the more general. So as long as the map sort of on average is chaotic, has this expansiveness property, this will be a good partition. It's a little harder to tell if, what's the balance between stabilizing, contracting areas where slope is less than 1, and expansion areas in an arbitrary map. So what we say is that some sort of measure of chaotic behavior would be like positively operative exponent. If that's the case, then this recipe will give you a nice generating partition. You'll have faithful encodings. So that's pretty easy. Basically, imagine applying to the huge space of one-dimensional maps. So we have good codes for those. You can sort of imagine the situation where maybe it's higher dimensions. It gets much trickier. In fact, in our research group, we're going over how you partition other kinds of maps, higher dimensional maps, not so simple as the cat map or dissipated Baker's map. So it's still some more sophisticated techniques let you sort of hunt around for some sort of good encodings. But now I want to give you an example that sort of shows you what happens if you don't have a Markov partition or generate partition. In other words, in a sense, you've picked a bad measuring instrument. So here's a construction that's going to lead to a familiar example we've already studied. So we'll look at the logistic map again, and also where it goes is fully 2-1-1, goes all the way up to the top. And there we had, if I'm just up here labeling the cells of the Markov partition we got, right? That was 2 states, all transitions allowed. But now what I'm going to do is not look at the sort of A-B partitioning. My instrument, for whatever perverse reason, I'm putting the decision point, it's binary, so the instrument's going to return 0s and 1s. And I'm going to put the decision point up here at, turns out, the largest inverse of a half. You'll see why in a second. It's a particular construction, but this is not, generating or Markov would be the decision point here. I'm going to put it up here. And the question is, what's the 0-1 sequence look like? We know that the logistic map at this parameter value has the largest Lyapunov exponent, it's most chaotic. We do the Markov partitioning, nice 2-state Markov chain, great. Calculate things. But now we're sort of relabeling things with this who knows what, at least initially. So we now have this partition that from 0 up to D, for most of the interval, it outputs a 1, and then occasionally for D up to 1, it outputs a 0. Okay. Well, we know that this Markov chain captures all of the sort of chaotic dynamics. There's this essentially, the AB alphabet is a good encoding, so we can study sequences over here to understand the continuous logistic map. So now the question of what does the 0-1 process look like, we can change that into a question about how this AB Markov chain generates the 0-1 sequence. So again, AB sequences give a faithful representation of the logistic map itself, and then to answer the question of what does the 0-1 process look like is really just a relabeling of this. And then we can say the relationship between AB sequences and 0-1 sequence to answer our question. How good or bad is that? Putting D up there. So here's the labeling. So, and you have to just kind of go through and convince yourself. So A goes to itself. So A goes to itself and also to B down here. And both of those are on 1, right? So states in here go to A or to B. Okay, so our head's inside the box. We can see the AB sequence. That's good. But both of those are transitions that the instrument's going to output a 1 on. So A goes to A on a 1. A goes to B on a 1, too. Same thing down here. B goes to A. B goes to B. I should say B goes to A. B goes to B. When B goes to itself, it happens on a 1. It's this set of points here. So B goes to B, B goes to A. So it's the upper piece here. That's why I chose the divider here. There's a piece of B that goes to B. Piece of B that goes to B. And when the instrument sees that, it outputs a 1. And then there's a piece of B that maps to A. And that is labeled 0. There's a piece of B that goes to A that's labeled 0. So the claim is, what I'm sort of arguing is that rather than sort of now try to answer this question on the interval, I can just study this hidden Markov model to understand the relationship between the output sequences and the continuous states. Well, no, I'm using the proxy of the internal Markov chain over AB because we agreed that was a good encoding. So we just have to study this. The relationship between the internal state sequences now and the 0-1 process is essentially the answer to this question, a way of analyzing how good or bad this partition is on the interval of the map. This should look familiar. Well, we talked about this. This is the simple non-unifilar source. And it will be a prototype we will come back to again and again and again. So remember some of the curious properties of this. So if you don't know what internal state the process is in, but then I tell you, oh, you just observed 0, you look at your model, you go, oh, I know, it's an A. From that point forward, though, the next symbol I can predict. with probability 1. I'm going to see a 1. No matter what transition state, I'm going to see a 1. So if I see a 0, I must see a 1. So this is sort of like the golden mean process, no consecutive zeros. But if I see a 1, say I knew with probability 1 I'm in state A after I saw a 0. Now I say, oh, 1. Well, you can predict it. Now I ask you, what state is the process in? Well, it turns out I didn't write it down. The transition probabilities here are 50-50, like the previous model we introduced. So actually, I'm exactly uncertain after the next step, after a 0. I see a 1, but I don't know which state the process is going to be in, A or B with equal probability. And then if I see another 1, it turns out a little bit of probability leaks over to B. Another 1 will probably leaks over to B. And we need to know what the internal state probabilities are to make a good prediction of the probability of seeing a 1 or 0 in the next time step. We have to know that. So as a consequence, as we see more and more 1s, our updated guess as to the internal state probabilities keeps shifting. These are different states of knowledge, and we have to keep track of them. And so it's actually just a few more steps where it's essentially, if I keep seeing 1s, 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 there's all this state information or predictive state information I need to keep track of. And that's going to lead us later on to construct an countable infinity of states for this, for an exactly predictive model. So there's some funny things going on here. So this is an example of how it can go wrong, right? The question I was trying to illustrate here is, rather than these nice encodings, Markovian or generating, just plop down some other point. Well, I picked one that's a nice construction. In this construction, R equal 4, we know what that asymptotic state distribution is. I can calculate the probabilities of these partition elements, transition probabilities, all in closed form. The net result, when you do this, is you get this simple non-unifilar source. Right? Remember, non-unifilarity was exactly this property. State, I should say, unifilarity was state plus symbol uniquely determines the state, and that's broken here. If I'm in state A, a 1, I can go either to A or B, so that's just broken. It's not unifilar. And that leads to this bad encoding. There are lots and lots of internal state sequences that lead to all 1s. So in other words, if I see all 1s, a lot could be going on inside that's not reflected in my measurements. That's bad. That's not a good encoding. Right? I can generate 1s just by staying here. I can generate a bunch of 1s and go down here and then generate a bunch of 1s. There are all sorts of internal state sequences. In fact, it's infinite to 1. This bad partition choice makes the mapping between internal state sequences to observed 0-1 sequences infinite to 1. We're throwing an infinite amount of information away. Not good. So again, you have to be careful about these things. Okay, so that's how it can go sort of haywire in 1 dimensions. Now I want to kind of talk about how it can go bad in higher dimensions. Again, just a little taste of how these things go. So remember the Henon map. That's this map of the plane. In fact, if notice that if it has 2 parameters, A and B. A sort of acts like the height value, the logistic map. In fact, if B is equal to 0, then Y is always 0. This goes out, and I basically have a little quadratic map. So we say the Henon map, when B goes to 0, is essentially the same thing as the logistic map. When B is positive, we have this sort of mapping, which we went through before. So I've got this kind of square here. It's not a unit square necessarily, kind of shaded to give us a sense of orientation. I have these 2 boundaries. So what this mapping does, sort of pictorially, is it picks up this square, it stretches it out, and folds it over, actually then turns it over, and then puts it back into the plane. And here I've got the dashed boundary of the original square. There are points in the square that map outside the square and actually go off to infinity in this case. There are points around the origin that map close to themselves, so there might be an invariant set in here. Okay. And you remember, what you actually put in sort of the Henon's original parameter values, 0.3 and 1.4 for B and A. You get this sort of horseshoe shape that lives just in here. And here's the picture of that. So the red is just a series of iterates. So that's what the unstable manifold looks like. And if you sort of recall the stringent sort of alignment that Markov partitions in 2 dimensions required, the Henon map completely violates that, because there are points on the attractor, and here I've just done a calculation for one example. There's a point on here that is, well, in the attractor, so it has an unstable manifold. That's where the things are locally spreading apart. But then the stable manifold comes down here and is actually tangent. We don't have this clean splitting, this nice uniform hyperbolicity that made the previous constructions work, where basically we're just looking at how unstable manifolds map to unstable manifolds and stable manifolds map to stable manifolds. This tangency, they come together, they're parallel, completely messes up a nice clean dividing like that. And that causes bad encodings. That's the geometric reason for bad encodings. And this kind of tangency, so-called, between stable and stable manifolds happens kind of typically. If I were just write down some Lorenz, Rissler, Duffing oscillator, van der Pol oscillator, this kind of thing happens all the time. So it's kind of bad news. Now there's sort of a guess, and people do try to make good partitions for the Henon map and other things. Then the hint was, well, it's kind of related to the logistic map as B goes to 0. So maybe for B small but not 0, I can still use the binary partition over x equals 0 in this case. That would correspond to putting the divider underneath the maximum of the logistic map. So there's some suggestions about how to do that. And then what you do is you try to correct your partitioning as you look at longer and longer sequences. So it's a whole industry looking at this kind of thing to figure out. So that's a typical way this goes bad. So just to sort of summarize things, so the last, I guess, the two symbolic dynamics lectures, but even before that, talking about probability and so on, is trying to set up not so much, a picture of how we analyze dynamical systems, but really to think about what the measurement process does and how a measuring instrument interacts with the dynamics. So I've given, some positive results that, amazingly, there can be these very nice, discrete valued processes that are great encodings of the continuous state dynamics of a system, but also a number of cases where this doesn't work at all. In fact, it's kind of typical. That sounds kind of bad, but they're good approximation schemes. The benefit when things work well is that we end up with this discrete valued sequences and their probabilities, discrete valued stochastic processes. Now you might say, well, maybe the message is kind of bad. We don't have always have these nice encodings. Well, there's just a really practical issue. Very practical. Forget all the math. When you go to DigiKey and buy the 16-bit analog to digital converter, you're discretizing. We have to deal with this. We have to understand, when we're looking at continuous state systems, what do these discrete sequences tell us? So I actually don't see the kind of the positive negative sort of story about symbolic dynamics is actually, it's not our fault that worked out that way, but it gives us some picture of when it can work and the criteria for when it works well. So hopefully there are cases you can do, and then there'll be cases where we just deal with this in discrete data. And I hope, it doesn't get too bad. I mean, if you had infinite precision analog to digital converters, maybe this wouldn't be an issue. But then, even then, you'd have an infinite amount of information you have to process. So there's even kind of a practical amount of data trade-off here that comes into play. So they're very practical issues why you want to study symbolic dynamics. Not just be the specialist who's trying to come up with these really very contorted codes for a three-dimensional smooth nonlinear map. It's just giving us an idea of what goes on. Measuring instruments interact with the system. I mean, that said that way, it almost sounds quantum mechanical, right? Quantum theory stands in physics as this unusual situation where we have to worry about how the observer interacts with the system, which Einstein didn't like that, right? Even what I'm arguing here is even in a classical setting, we have to worry about the measuring instrument and what it contributes or doesn't contribute. That case of the simple non-unifilar source, the non-unifilar partition, if you will, we're going to see that bad choice of measuring instrument actually adds complexity. It throws away randomness that the system has generated, and it adds apparent structure and complexity. Both of those are bad. So here we are. Right. What are we going to do with this? So this is a multi-staged argument that we deal with discrete valued stochastic processes. And the questions are, what can we learn from them? The constructions I just gave actually required us sticking our head in the box again, because I had to see how these partition cells mapped into each other, and I was using the map to do that. Imagine that you just made a bunch of measurements. This is before you've even started, you haven't even been studying your experimental system for a while. I just give you a bunch of data. You don't even know what the dynamic is. You've got the time series of measurements. What are you going to do with that? So that's kind of the burning question now that we reduce this down. We have some appreciation of the complications. Also, the hopeful picture, maybe we get lucky with a good partition or know how to construct them. Simple models can be analyzed very straightforwardly. So it's, so what do we want to do with this resulting process? A whole range of questions. What we're going to focus on is how to measure from these discrete valued stochastic process how unpredictable and random they are. Over what range do we have correlations? Like I said before, for that simple non-unifilar source, there actually are a countable infinity of states that indicates that that bad measuring instrument induced infinite range correlations on the logistic map that at that parameter otherwise looked like a fair coin. So we need to, what do we mean by correlation? What do we mean by structure? And then, okay, so this is kind of like maybe quantitative or mathematical statistic set of questions. We're not going to use statistics so much as information theory, but how do I build a model? Right? I mean, we're the recipients of all this data coming out. How do we build a model? What does it mean to build a model? If I give you the data, is this a first order Markov chain, second order hidden Markov model, what? And what do we mean by state anyway? If I just give you a time series, what are the effective states of the process? You know, if I can discover what the states are, maybe then I can then figure out how they transition to each other and get a dynamic out. So is there a way that I can build these various kinds of Markov and hidden Markov models just given time series data? Or even perhaps more ambitiously, is there some way that by looking at these finite resolution measurements of our process, I can actually reconstruct the internal state space, continuous state space, and say differential equations that are governing the system from the data? So these are big questions. So the first thing we're going to do is mostly quantitative. We need to start thinking about, well, it'll be familiar since we've spent so much time talking about chaotic behavior, like how chaotic things are. We have the Lyapunov exponents. But there are other issues. How structured? What is correlation that we have to get to? So we're going to go through elementary information theory and sort of tease it out. And we'll start reading the Cover and Thomas Elements of Information Theory book, just the first few chapters of that. And then extend that to deal with arbitrarily complex, arbitrarily correlated processes over discrete alphabet. Introduce some new quantities from information theory. And then sort of by the last week, we're going to say, there's some problems even with that. It doesn't actually take us to building models. So the spring quarter is going to be, we'll focus on sort of the failings of information theory, which has many positive things that contribute, but it doesn't really tell us how to build models, and that's what we're going to concentrate on in the spring quarter. So pretty much at this point going forward, we're going to study processes over discrete alphabets, stochastic process over discrete alphabets, and try to answer these questions. And I hope to convince you there are positive answers to all of these things, but we need to think harder about what it means to make a prediction, build a model, what are states, what is information? One of the points of the information theory introduction is information is not a unitary concept. It depends on the context of use. And so we're going to end up with a hierarchy of different information measures. Some relate to randomness and unpredictability. Some relate to memory. Some relate to correlation. Some relate to synchronizability, how easy I can figure out what the internal states are, and so on. There'll be a whole hierarchy of these different kinds of information. And even then, it won't be enough to get to model. So. Okay, so that's it for today. I guess I'm finishing earlier and earlier. Oh well, that's fine. But now questions. Of course, these are...
So when you're saying the reading is just the lecture notes, just look ahead at the slides for the next.
Actually, in this case, yes, which means that, right, tomorrow I'll put those up, but if I'm not, if I'm remembering correctly, it's the first chapter or two of Cover and Thomas. I kind of mix and match these lectures each year, dropping examples, adding stuff in, so these tie-ins. I'll have to go check, but actually I think the next lecture is elementary information theory, so it'll be the first chapter or two of Cover and Thomas. Just read
We are
them.
making that transition.
Yes, we are making the transition. I declare we're making this transition. Then I'll go look at my notes and realize I'm forgotten, but yeah. Okay, good. See you.